Hello, Honors Chemistry, and welcome to your Chapter 10 review, where we're just going to highlight some of the important tidbits from Chapter 10, including, well, primarily Lewis structures, right? There are rules for a reason, right? Obviously, if you are really well practiced, like you've done every single EOC, you've even done the even EOCs just for extra practice, you've done the entire review packet, and you've checked them and you've gotten them right. All right, yeah, you at that point may have reached a point where you don't need to follow the rules as written, okay? Until then, though, follow them, right? If you follow the rules, you're most likely to get your structures right. If you choose to try to shortcut it, you're going to miss a whole bunch of them, and then it's ridiculous because you could have gotten them right if you followed the rules. So I don't know how to implore enough. Please follow the rules, right? So the rules start with, right, putting your atoms down, right? Then you're going to count your valence electrons. And then you're going to, right, you're going to draw bonds. And then you're going to fill valences, fill octets or duets if we're talking about hydrogen, right? And then you're going to, well, then you'll sort of redistribute as needed, I guess, would be that next step. Forming either multiple bonds or expanded octets, whichever is necessary. So redistribute as needed, right? And then double check. Right? That's that super duper important last step where if you do that, right, you're going to get it right. You just have to make the time to do that. All right, so let's do some practice together. So let's say that we were given all of these and we could be asked any of these questions. We could be asked, what is the electronic geometry, or what is the molecular geometry, or is the molecule polar? All of those really mean what? Right. Any one of these questions really means draw a Lewis structure, okay? We have to do some interpretation after that, but all of these questions start with draw a Lewis structure. So let's go ahead and start with one, right? So for silicon tetrachloride, first we need a formula, right? So this would be SiCl4. So we count our valence electrons where silicon has, right, 4 plus, we have 4 chlorines with 7 each, which means we have 28 plus this is 32 electrons, right? So we'd start by putting our atoms on paper, silicon, chlorine, 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 right? And we would bond them, and that costs, right, that costs 8 electrons, which leaves us with what? Right, 24, right? And then we will fill my chlorine valences, that's 6 each, times 4, which means what? Right, that's 24 electrons. So we've actually used all of our valence electrons. Now we go and check valences, right? This chlorine has access to 1, 2, 3, 4, times 2 is 8. This chlorine has access to 8, right? It's symmetrical all around. Sulfur has access to, silicon, has access to 2, 4, 6, 8. Check, right? It meets all the criteria. This Lewis structure is done. Now, if we wanted to answer some follow-up questions, we would apply the Vesper table, right? Where, like we said in class, right, this is the number of groups around the central atom, where this is going to be bonded atoms and lone pairs, right? And note that it's around the central atom, okay? And then we can deduce the electronic geometry and then subsequently the molecular geometry. So currently we have a central atom with 1, 2, 3, 4 groups around it, right? Which means that puts us here. And then we'd scroll over and see, oh, are there any lone pairs? No, which means that it's this. So you would say its electronic geometry is tetrahedral, its molecular geometry is tetrahedral, and it is nonpolar. Yes? All right, so let's go ahead and do another one. Let's say we wanted to do phosphorus tribromide. So we'd have P, Br3, and so then we'd go through all the same steps, right? Phosphorus has 5 plus 3 times 7 gives us what, 21, 26 electrons. Phosphorus, bromine, bromine, bromine. So that's minus 6, so we've got 20 left. Let's fill our bromine valences. So that's 3 times 6 is what? Right, that's 18, so minus 18 leaves us with 2 left. Put that there. We've used all of them. Now let's double check, right? Bromine has 2, 4, 6, 8, and 8, and 8. Phosphorus has 2, 4, 6, 8. All the valences are full. Let's check the number of electrons. 8 plus 8 plus 8 is 20. What? 8 times 3 is 24, 25, 26. Yes, we've done our double checks. This structure is right. Let's go ahead and use our VSEPR table, right? So if we take a look, we have a central atom again, surrounded by 1, 2, 3, 4 things. Yes? Central atom surrounded by 4 things. So if I go over here, I'm going to go down here again, but I'm going to scroll over and see that, oh, it actually falls under this category. So its electronic geometry is tetrahedral, its molecular geometry is trigonal pyramid, and it is polar. Yes? All right. So selenium has 6, oxygen has 6, which means we have 18. Minus 4 for bonding leaves us with, what? How many would have 4? So 14. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So minus 12 leaves us with 2. We've used all of our electrons. And then what? Right. 2, 4, 6, 8. 2, 4, 6, 8. Oxygen is fantastic. Selenium has 2, 4, 6. We got to do something. So we're going to redistribute. We're going to take a pair off of here and turn it into a double bond, right? Now let's stop and look again. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Now we have the right number of electrons and everybody has a full valence. This is the right structure for selenium dioxide. So if we go and apply, right? Oh, I'm just going to write it down. Well, fine, let's just do it. All right, so we have a central atom, we have 2 groups, and we have a lone pair, right? Which means that we have a central atom with 3 total things, right? One of which is a lone pair. So to be trigonal planar, bent, polar. Yes? All right, next up. Xenon tetrafluoride. Xenon tetrafluoride. Xenon has 8, and no, they don't form compounds often, but they do sometimes, right? So xenon has 8 plus 4 times 7. So that's what, 28, 36. Xenon, fluorine, bond, 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 minus 8 leaves us with what, 28. And then 1, 2, 3, 4, 5, 6. So that's 6 times 4 is 24, which means 4 valence electrons left. All right, so that looks weird, right? But let's count and check, right? 2, 4, 6, 8, full, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Xenon has too many, but do we have the right number of electrons? And that would be 8 times 4 is 32. 34, 36, right? That is the right number of valence electrons, right? And then we would go double check, is xenon capable of having an expanded octet? And the answer is yes, because it's in period 3 or greater, right? So we could have an expanded octet. So in terms of determining our structure, right, we have a central atom that has 1, 2, 3, 4, 5, 6 total groups around it. So we go over here, 6 total groups, right? 4 of them are atoms, 2 of them are lone pairs, so we'd say it's octahedral, square planar, nonpolar. All right, last up, sulfur tetrafluoride. So let's go ahead and do that one over here. So sulfur tetrafluoride, that's SF4, right? And so sulfur has 6 plus 4 times 7, so that's 28. 28, 34. We have sulfur, 1, 2, 3, 4. Right, so then we would subtract off 8, which leaves us with 26. And then we'd go ahead and fill our fluorine valences. So that's 6 times 4, so that's 24. And we'd put that last one on the sulfur, right? And then we would double check, right? So 8, 8, 8, 8, 2, 4, 6, 8, 10, too many. But let's double check our electrons. So 8, 8, 8, 8, 32, plus that makes 34. So that's the right number, right? And is sulfur in period 3 or greater? Yes, so it can have an expanded octet. So let's go see where this falls on the VSEPR table, right? We have a central atom with 1, 2, 3, 4, 5 total groups. So 5 total groups, right? 4 atoms, 1 lone pair. So this would be called seesaw and it would be polar. Yes? All right, fantastic. So in terms of polar and nonpolar, do be mindful, right? Implications there mean if it's polar, there are stronger forces of attraction between molecules, right? And if there are stronger forces of attraction, that leads to things like, right, higher boiling points, higher melting points, and higher viscosities. And things with dissimilar polarities, right? So things that are polar do not mix with things that are non-polar, right? It's like they have to share a way to interact with one another. All right, thanks for listening. Be good, and I will see you soon. Bye.